we'll start from like we'll start from like a really basic point of view, and like work out like the entire justification for like why we want to be implementing any type of control system at all. And then yeah, we'll go ahead and implement it on the robot, and then we'll see the effect that it has. So to start with, I'm just going to be talking about controls theory like more abstractly. It should show my paint screen. I'm just going to see if it does. I think it's working, right? Just tell me if paint is open. Okay, so basically, um, what is like like to solve any problem, we first need to identify what the problem is. And in control, what the problem we want to be solving is, uh, we want to take some human input. So we want to take some human input up here. I'll just like label it I, and then our robot. So then like our robot will have some robot input over here. I'll just label this R, and then we want to take our human input and transform it into some robot input that it understands. And so like why are we doing this, right? The reason why we're giving the robot some input is because then the robot internally will like it's called actuation, where it will like spin motors, for example, or activate pneumatics. In our case, it will just spin motors, and then it will change our state S, right? Like so, I'll give you a more concrete example of what this means. If our human input here is like if I just draw like a controller, right? If we move our controller joysticks, we want that to correspond to some to some like robot input over here. In this case, that would be like motor voltages, right? So like I'll just like write V over here, for example. We want to spin the motors as voltage. This is what we've been through already, and then from those like by changing the voltages by actuating the system will respond, and the robot will either accelerate or deaccelerate depending, right? So like if we draw like a little graphics here, drawing on computer is kind of hard. Let's just imagine those are wheels or whatever. Then like let's say like our robot will be getting faster, right? This is called an open loop system, where the only thing that's happening is we're taking our inputs from this side, and we're using only our inputs to decide to like actuate the rest of the system. And it's open loop because information data is only flowing in one direction, right? So it's starting from our inputs over here, and then it's flowing to our robot, and then from our robot it's affecting our state, but nothing is like being put back in the system. So why why is open loop control like not necessarily optimal, right? The reason for that is because when you're telling the like in open loop control, you can only direct to like your sorry. Okay, wait. I'll back up 1 second. This step here between our inputs and our robot inputs, this is where our control system lies. So all of our control logic is just some function over here. Like I'll just call it F. And then it takes our inputs, and then it gives us our robot inputs. Right? But with this system, the only things that we're able to control are we're not able to abstract in any sense. And I'll show you what that means, right? Essentially, that means that our inputs are only allowed to take a form that our robot inputs allow. So in this case, we can't actually directly control the speed of any of our wheels, even if that's what we would like to control. The only thing that we can actually like control is like this the voltages on the motors themselves. That can be like, first of all, when you're designing a system, you're often not thinking in terms of the like actuation points, you're thinking in terms of like different variables, right? So when I'm thinking about my robot driveways, and if I'm tracking a path, obviously like what I'm keeping track of in my head is how fast the robot's actually moving, you know, like on its left side, on its right side, and I don't like care, and I don't necessarily know what voltages are specifically being applied to the motor at any given point. And the problem with that is that in open loop control, you're not actually able to control the variables that you like. You're not able to manipulate the variables that you might want to, right? So in this case, I can only manipulate voltage, and I can't actually manipulate directly the robot's wheel speed. So how do we solve this problem, right? And the reason for that is because, again, it's open loop system. So any information that we're putting in is ultimately being funneled through from the robot inputs into this state, right? And there's no there's nothing going around. The way that we solve this problem is that we take sensor readings and then we make this a closed loop system. So our sensor readings, I'll just call this let's say Y for now. And with sensor readings, what we're able to do is we're able to funnel this sensor readings. Okay, I might use a different color here, but we're able to funnel those sensor readings back into the system. And so when we're mapping from our inputs to our robot actuation, it's able to take into account our current state as well as known data, and that way we're actually able to even though we could only still even though we can still only control the robot through the specific actuation points. So we're only able to still we're still only able to change the voltage of the robot, right? We're still not able to directly just magically set a speed on each of the wheels. The internal sensors or sorry, the internal logic itself is able to receive a desired speed as an input and bring us to that bring us to that point, and that is the whole theory of control, right? So I'll clear this up a bit. So if we have inputs here, I just want to draw again, but be a bit more clear with the full loop system, right? So we have our human inputs over here. And then what we want to get is we want to get our robot inputs. And normally this is you use, oh crap, okay, so that's I can't just, that normally we use U to represent our robot inputs. And then all you have to remember is that this is just our voltages on our motors, right? And then from here, there's so this step right here is where our control logic lives. So this is our control function F. It lives right here, and then from our from our robot actuation, it will spin the motors or do something, right? And then that will lead to some state change within our system. So this will be state change, I could say I use S X, and then this is where physics, right? So this is where the physics and you know the external real world stuff happens. But then from here, so from here we want to feed. Why is this green? Okay, wait. From here we want to feed back our current state. Sorry about this. Let me delete. Okay, there we go. From here we want to feed this back. We want to feed our state back into our robot actuation, and then that way we're able to that way instead of only being able to so with open loop system we're not actually controlling our state, we're controlling our actuation points, right? But what we want to do is we want to control our state. We want to if there's an arrow from our inputs into our state, we want to actually control our state. So our whatever, however that's defined, and through a closed loop system that's how we're able to achieve that. So let's talk about some actual practical implementation details from this abstract theory. So the question now is how do we design this system function in a way where we can take any where we could take our input as however it is. So in this case it would be controller joysticks. How do we how we're able to, so how do we take that and then output some robot input, right? Robot actuation that will allow our state to get to get to where we want to go. So in a sense it's what's that's the entire theory behind, sorry, that's the entire problem statement behind control theory, and then that's what we want to address right now, right? So first of all, like we want to figure out how does our system respond to changes. So again, let's go back to the example of our drive base. Let's go to the example back to the example of our drive base with its wheels. Um, we know that like let's say like so like from a basic point of view, we could say that like we could figure out like how it responds to changes in a simple way just by saying that um, if if our voltage is high, so like I'll say like if our voltage is like high, um, it speeds up, right? And then if our voltage is either like low or negative, like the friction will slow it down, or like the acceleration on the wheel itself will slow it down, right? So if we want to like we know that if we want to, let's say like our robot speed right now is like you know like 20, like just using some arbitrary variable, and then if we want to set it to like 50, then we want to like this means that we want to increase our like voltage, right? And then like vice versa, if we want to like slow it down, then we want to like decrease our current voltage. Okay, so now that we know, so like using this information alone, are we able to like design are we able to design this like uh state function, this function over here, in a way where it will like let our actual state reach like our desired state? And the answer is like yes, with a few conditions. So like um the key here is that if we have like okay, let me draw this out more explicitly, and then so to better illustrate the example, let's say like we have our like this is our like on the y-axis, this is our voltage, which I'll say is like w like that, and then this is our, and then here let's say like this is our robot, like our speed, right? We know that like if we increase our voltage, then our speed should always increase as well. Like let's just say like this is a static situation, right? So not factoring into like necessarily like acceleration right now, but if we increase our voltage, then our speed should increase as well. So we don't know like how this function, so like let's say like this is just like a normal function, right? Like f of, why is paint so annoying? Okay, so f of x is equal to, like f of v is equal to s, sorry. Even though we don't know like what this function looks like explicitly, we don't know if it's like linear like a line, or we don't know if it's like we don't know like if it's like some weird shape like this, for example. The thing that we do know is that it has to be like if you increase your voltage again, your speed should always increase. So it can't be a shape, for example, like this, right? Because if we're like, let's say this is some voltage here, and then this is some speed. If we increase our voltage, it makes no sense that our speed goes down. Like, if that makes sense, right? And then in these types of situations where you have like some like some I guess faint idea of like what your function is, but like you know for sure that you know for sure like some properties on it, and specifically like in this case we know that our like derivative of like whatever this function looks like it could be like semi flat like this, and it could be like completely irregular, but we know that like the slope of the function at every single point, if that makes sense, like if I'm just drawing like slope lines, we know that the slope is always negative, so we could say that dv over ds is always, we know for sure that it's always greater than zero, right? And just from this point, we're able to like write some code to control our robot. So how are we able to do that? Let's talk about state and error. Okay. Okay. So does this all make sense so far? Like where we don't have like where we don't have, so in this case, PID control is very good when you don't have complete information about how your so like how your actuation, like if you don't know how exactly your actuation affects your state, but you know like some basic properties from it, you can derive you can basically like use this PID method to like best approximate your correct input. Does that make sense for everybody? Okay, great. Then we can move on. Okay, so basically okay. So let's say that we want to get to, okay, let's say our current state right now, so let's say our current speed right now is, I'll just say 20, right? Like, let's say our current speed is 20, like, it could be whatever unit, okay? And then let's say the way that our input works is that we want to find a way for our speed to go up. Like, let's say we want to like accelerate 10 inches per second, meters per second, whatever the unit is. Let's say we want to, so like our current state, I'll say is like X over here. And then if we have like a state that we want to get to, let's say like we want to get to 30 like inches per second, like that, right? This is our reference state R. Okay, so we're currently going at 20 meters per second or whatever, and then we want to get up to 30 meters per second. Okay, so how do we do that? We know that if we want to, we know that like if we want to like increase our speed, then we always increase our voltage, and if we want to decrease our speed, then we always decrease our voltage, right? So the most fundamental like type of or subset of PID control is just direct proportional control, where we are saying that if our so like basically like the statement here is if our like okay, so we could first of all like we could take our error in our current state by taking like our reference state subtracting our current state, which will tell us like what the discrepancy is. So in this case, our reference minus our current state x is equal to 10 like, I don't know, like per second, right? And then this one we're going to label like our error, right? Our current error. Now, if our current, like the most simple one, right, is just saying if our current error is positive, like if it's positive like this, then we want to like we want to increase our like current like input. So we want to go if our error is positive, then we want to make our like voltage positive, right? So our input, like which I'll just label U over here, is equal to like some constant times our current error, right? So like this is our constant of proportionality because our input in this case is proportional to our error. Now if we take this and just like implement it in code, which is which is what we'll do right now. This is the key part of the PID control, which is our controlling a robot input based on the proportionally based on the error. So that's kind of the theory behind it, and then like to implement that it's not too bad. So if we have like if I just write a function like void control, right? What we need to know is we need to know like let's say like we will just use double for all of them. So like as the big store shape, double like current state, double like reference state, and then double like constant of proportionality, right? So like our proportional constant, and then all we want to do is we want to take like our error is equal to reference state subtracting our current state. And then we want to return, so then we want to say our input is equal to our proportional constant times our error, and then we could just return our input. Okay. So what this will do is, I'll make this here. Now we have like our a proportional control, right? But the issue with just direct proportional control is that we're not taking into account so for example like again going back to this example where our previous speed was 20, what happens if we know, like if let's say we know our previous input, right? Like if we know that our previous input, let's say was like 50 out of 50 on the motor, right? So like 50 I think it's like millivolts or whatever. We could just say like 50, like let's just say it was 50 volts, right? If we know our input was 50 volts, and then let's say like our proportional constant was relatively small, so that our input here would actually like let's say like if our proportional constant was like 2, for example, right? Then if we take 2 times 10, then that would give us like 20 as our input, right? But then 20 is actually like less than our previous input. So we know like for sure that like inputting, like if we set the motors to 20 volts, that it's not going to go faster than when we set it to 50 volts, and we want to set it so we want to make it so that like we want to make it so that we're accelerating, we're not deaccelerating, right? So how do we take that into account, right? Well, what we could do is we can in this next step, what we can do is we could take our previous input into account as well, where we are if we include our previous input into the equation on like this side, instead of just like setting our current input directly proportional to the error, we can increase or decrease, like what we should be doing, right? In this case, we want to like increase or decrease our current input based on whether so based on like the sign of the error. And then we could use our previous input as a reference. So if we say that like if we're going at 50 volts and then we're going 20 meters per second, again referring back to this function, like let's say like 20 is here, so sorry, 50 volts is here, and if our function like looks something weird like that, we know that like there's some like number over here, like let's say maybe it's 100, maybe it's like 70 or whatever, where we're able to like get to our 30 meters per second target, right? And then using this, we're able to implement like what's known as integral control. I don't think that sorry, like integral control would be like you're going to be summing up your error over time. But I think that like a better implementation of this in this case would just be like to increase or decrease our previous input based on like the sign of this error, which effectively like amounts to the same thing. But I think it's like more intuitive way of implementing it, because we can, going back to this function, so like I'll just call it modified proportional control, right? Going back to this function, if we change if we just like add a like parameter in this function, so like double like previous input, and then same thing double, and then we keep our like proportionality constant, then our error stays the same. Our error stays the same, and then all we're doing is we're doing error input change is equal to proportional constant times error, and then we're just returning our previous input plus our input change, right? So like I mean, yeah. So like if I write it like okay, like this. And all of a sudden, we're taking not only our previous state into account, we're taking our previous state into account, which is like the sensor reading. We're also taking our previous input into account, right? So we're like, it's like, if you had no idea like what these numbers were, you're just saying like, here's my system. You're able to like, let's say there was like a black box, right? And then you have no idea like how the black box works. It's just like you input me a number and then I'm gonna like spit out a number, right? So if you know that like I'm inputting 50 right now and I'm getting 20 out of this black box, right? So like if 50 goes in into this black box, then it's like going to give me 20. And then I also know like the fact that we mentioned about the graph, right? Where like it's like a positive derivative, and I'm saying that I want to get like 30 out. I want to get like a 30 out of this box. Then I could just like increment my like input, or based on like my previous input, based on like how far off I am. So like if I start with like 50 and then I get 20, then I might try like 70, for example, and so on and so forth until like I'm able to like I'll just jump from like here, for example. So like this is like 50 and this is 20, and then let's say we're trying to get to here, right? So I might like jump around, go up here, and then all of a sudden my input is too high, and then I know that, right? So I could go back, and then we'll find like the correct we'll find the correct set point that gets us our desired output. Anyway, so if I just take this like this code, and then let's say like okay, so for like our proportion of proportionality, I want to make this like in the case of direct proportional control, you want to make this like relatively high based on like what units you're using and stuff like that. This is something that you just tune on your robot like through trial and error generally. In this case, because I'm like taking this as a sum over time, so I'll just like make it kind of small so that I don't blow up my robot, just in case. I actually don't know like what good constant is. 0.1 sounds okay. Does it sound okay? Yeah, I guess it sounds okay. And then what we could do is we could, so like going back to this code, right? So like this is the code that we wrote like all the way back, which is like all this is the open loop controller, right? So I wish like paint that you like, can I just make this bigger? Yes, I can. Wait, no, that's not what I want to do. Wait, what? What? Sorry, one second. Can I make my thing bigger? No, that's not what I want to do. Okay, whatever then. Anyway, okay, so here's some one frame, right? If we go back to our like, if we go back to our previous example where we had, what was our previous example? So if we have just our inputs and then we have like our transfer function over here, and then we have our like state inputs. What variable did we use? We used like u generally, right? Over here. Our open loop function is, and then this goes into our state. Then our open loop function looks like this, and this is what we had written before. Now what we want to do is we want to like grab the sensor inputs and then feed it back in. So in the code, it just like looks like this, right? So we are, the important thing is that we're feeding our previous inputs. In this case, we're also feeding our previous inputs back. That's what I wanted to point out, right? So we're not only feeding our previous state back into our inputs, but also we're feeding our previous inputs back into our inputs. Because that seems like the wise thing to do. So we want to store our previous inputs, which is like right here. That's good. And then we want to store our, and then we want to grab our, what's it called? We want to grab our, like, current readings, like our current speeds. What we could do for that is like we could just go double left speed is equal to left. Holy, this is like kind of fast. Very close. So I'm just gonna average the left front and left back velocities. Just like this. And copy this down here. Change this to left to right. Right speed. Okay. So now instead of just taking these, so like these are our inputs up here. What we want to do is like, so these are our controller inputs, right? We want to update our controller. We want to update our motor inputs, like our actuation points, based on this control function. So we could just call it up here with double like left double left power is equal to okay, so then we just go modified proportional control onto our, so our current state, right? So let's talk about like these variables in the implementation. Our current state is going to be the speed that we want, right? So like if we're doing left power, then this is going to be the left speed, like our current left speed. And we're going to, our reference state, so like our reference state is the control input up here. And in that case, and in this case, that's going to be our left. It's going to be like our left vertical plus right horizontal. And then our previous input, finally, our previous input will just be our motor, our previous like left motor power, right? So something like that. And then we plug that in, and we grab our. I think I spelled it wrong. And we grab our like left. We grab our new left input, and then we're going to. So we're going to do the same thing on the right side. This is our left input, and then this is our right input. This shouldn't change. Should just go to subtract. And then this one will just go to 2, for example. And then down here, this has to be declared up here. And then down here, we're just going to plug these into our motors. And then we plug, so like these go into our, like we just store these over here. Then we plug these into the actual motors themselves. These don't need to be here. We plug these into the actual motors themselves. And then because this is running on a loop, this will, I spelled this wrong. This will like, this will cause the control loop that I was talking about before. So let's see this in action. I'll just like build this and then plug into the robot now. Is there any questions about how the system works? That would be a good time to ask. It would just take a second to build in. hopefully this doesn't blow up the robot. So there's a chance that if you like guess this like proportional constant wrong, that you'll like blow up a robot or something like that. You kind of have to like mess up like quite a bit to. Yeah. So like anyway, just if like anything weird starts happening, just turn off your robot and then just like guess a lower constant. That generally works. Okay. Should we go first? Okay, does it look like my right side is what? Doesn't look like my right side is spinning. Oh, and I think I have one of the motors in the wrong spot. Oh man, that's not gonna be fun. Let me think. Let's check my... Okay, wait, hold on. I'll show this for now. Okay, so switching over to my camera account. Wrong camera. Okay, so one thing to note is that once you have like control, right? So like now that we're like setting speeds and not just setting inputs, my robot becomes like incredibly hard to move by itself. So like if I turn off the robot, you can kind of see that like I can just push my robot around, right? And it doesn't like it's fine. Okay, so if I run the program though, is it running? Yeah, okay, so if I run the robot, so like if I turn on the robot, you can see that like, okay, I'm pushing it right now and it's like not actually like the wheels are resisting me, right? And it's on carpet right now, but if it was on like tile or like flat ground, it would like, because right now it kind of slides because it's on tile and stuff. But yeah, it's not, it would like, it locks the position because it thinks that, so if I have a control over here, this is pretty cool, right? If I have the controller right here, my inputs are 0, right? And before that just meant that, like, this is what I meant by the actuation points. Where before, the only thing that we could control a robot through were the actuators and the voltages on the motors, which meant that, like, all we were telling it was that, like, just go 0 voltage. Right now, like, the way that our code is interpreted is the robot thinks that it's telling it to go 0 speed, right? And 0 speed is not the same thing as 0 voltage, because if there's external force, or, like, for example, if this was on a hill or something, 0 voltage would mean, like, don't apply any power to the motors. But some like actual voltage up here means that like sorry 0 speed means that like no matter like what other external force is applied, so if it's my hand or if it's a hill or something like that, actively like try to like keep the speed at 0, and like that's why you can see it was resisting. Okay, so one of the things that I think is not working is that like I think I have like some of my motors like wired incorrectly, because it's like driving. So like the left side clearly works. The right side, I think I have like, I think one of the ports is incorrect. But even still, you can see that. Okay, even still, you could. I think like it still drives. I guess it would be a better demonstration if I had like an arm, like we saw Alan build prior, or something like that, because you could see that it would actually be like maintaining a position. Like you can kind of see that with in this case because it's maintaining the 0 position, but it's kind of hard to show that like it's maintaining like a speed set point, if that makes sense. But yeah, I hope that this gives you a good illustration of like what control is for. I'll try to figure out the motor issue for next time, obviously. And it's okay. So yeah, it's getting just 5:40 for today. If there's any questions about like controller, like why I think that like the most important thing here is not necessarily how to implement it, because that's something that like if you're interested, you could like reason it out for yourself even, right? But more so like why we're implementing control. That's something I try to like explain from like the ground up, starting from like what we're able to control without feedback control, and what we're able to, like with only feed forward control, like the only things we're allowed to control are the voltages. With feedback control, we can kind of control any variable that we can A, measure, and B, model. And yeah, so and then this demonstration is kind of like a demonstration that like we are in fact setting the speed of the motors now instead of just setting the voltages. So yeah, if there's any questions about that whole like that whole idea, I think yeah, now would be a great time to ask. Okay, I hope it was, yeah, I hope it came out clearly. Next time we could talk about, like, we could go more in depth into sensors, and next time about like how to like, or we could go talk about like system modeling and then how to like tune out sensors for the next time. But for today, if that works with everybody, sorry, if that works with everybody, then like I think we're good to go. And we could just call it here. Just stop the OBS.